Institute of Engineering and Technology.
Hello students, today we are going to consider our last part of Fourier series, representation of function. We already gone through the introduction of Fourier series, the general case of Fourier series, how to represent even odd natured function with help of Fourier series. Today's discussion is a special case where our function is defined in half range of given interval. For example, it is defined for 0 to 1. We have two possibilities to represent it. It may happen that it is a choice of cos function or it is a choice of sine function. Both are wave natures, and then how to use this thing with help of half range Fourier series, that is our discussion for today's talk. We'll try to cover this thing with help of extension. What our center of discussion is, we have half range of the function, we'll extend it into full symmetric range, and then we have the freedom to consider that function as even or odd. We know that if that function is even, then it can be represented by cos function. If it is odd by nature, it can be represented by sine. So this is whole idea about half range Fourier series. You can consider half range Fourier series as the easiest case possible for calculation, as where we don't have to go for any check whether it is even or odd. If the question is that find Fourier half range cosine series, that means by force you need to consider that given function is even. If it is given that find half range sine series, that means by force you consider that given function is odd. The reason is it is defined only on the half range. We are extending in the second half in such a way that overall nature will be odd or even. So let us start our first discussion, that is how to consider this half range Fourier series. So the idea is this thing, that if my function f of x equal to y is defined only on the half interval 0 to c, half it is in the context of that symmetric range minus c to c, then we can extend it in two different ways in that second half minus c to 0. So on minus c to z, we can minus c to 0, we can extend it to be even function in such a way that it is even on minus c to c. So this is the first possibility. Second possibility is I can stretch my, or I can extend my graph in minus c to 0 in such a way that the overall function is odd by nature. How is it possible? Let us consider a graph of parabola x square in 0 to 1. So 0 to c is given. Now the first possibility is how I can extend my graph in that range minus 1 to 0 such that overall graph will look like even function. So this is the reason why the blue part over here, it is imaginary part, it is our imagination that it is happening in minus 1 to 0 in such a way that that overall graph will look like parabola. So this is first extension. So now you can find even series representation for minus 1 to 1 range. And then if you take x equal to 0 to 1, it will give you answer of your required function in the given range 0 to 1. Similarly, I can extend it in minus 1 to 0 in such a way that it is odd by nature. So by same argument, in minus 1 to 1, now it is odd function, it can be represented by sine graph or sine function, and then you take input from 0 to 1 to represent this parabola with help of sine graph. That means now we have two different choice. We can use half range for sine, we can use half range for cosine also. Depending on the requirement of solution, you can take any possible case. Let us consider our first part, that is a half range as even or odd function. Suppose I consider my function even function in interval minus c to c. That means my function is defined on 0 to c by any random function, and I am stretching it in minus c to 0 in such a way that the overall function is even. So it is known as even extension, or it is known as half range Fourier cosine series. Why? Because ultimately it is represented by cos function. So its Fourier series will look like this. See, there is no difference in between even function and half range cosine series. The only reason is this series is valid only for 0 to c, whereas the previous case even function was valid for minus c to c. So calculation is almost same. Here again I am taking coefficients a0 and an defined in our regular way of even function. Now suppose my function is odd from minus c to c. That means in definition of minus c to 0, I am extending it in such a way that the overall function minus c to c, it will give you odd function by nature. So it is known as half range Fourier sine series. Obviously it is known as sine series because it is now odd by nature, so it is represented by sine. So again it is defined by our odd function in minus c to c, but remember here x is only and only valid for 0 to c. Again the values of bn is as per our calculation. So now let us consider our first example. Here the function is given by x square from 0 to 1 and I want to represent it with help of Fourier cosine series only. See, here we have many possibilities to represent it in case of Fourier. If I consider this as a general case, my answer will give me sine and cos both in the final representation. But now I can use my smart trick that I will extend it in minus 1 to 0 in such a way that it will become even. And so I can represent it only and only with help of cos series. It will be very interesting to see what is actually the graphical difference in between these two. Because in some cases a solution's requirement is to give function only and only with help of even. See, there is no relation with x square over here. Later on I will represent same x square in this range 0 to 1 with help of sine also. So don't get yourself confused over here. There is no check for even and odd function. These examples are in fact the direct examples of Fourier series. If it is given that find half range cosine series, forget about function's nature. Consider given function as even function. So I will treat this whole situation as even. Now I am taking interval minus 1 to 1. The reason is it is now stretched in that minus 1 to 0 parts in such a way that overall function is even. So I will use my regular calculation of even function. So it is depending on a0, an, value of c is equal to 1. So value of a0 is 2 by c 0 to c f of x. So it is 2 by 1 0 to 1 x square. Answer of coefficient is 2 by 3. Now what will happen if I consider the value of an? Value of an will come with help of Leibniz rule. It is x square into cos n pi x. I am taking Leibniz rule. Here again the first bracket is for derivative, second is for integration. We know that how to deal with this situation. I am taking u equal to x square and v equal to cos n pi x. So first bracket u as it is into v minus derivative of previous first in first bracket and integration of previous second in the second bracket, and up to so on it will go from 0 to 1. So ultimately you will get idea that how to represent this with help of cosine's values. So I am taking input 0 to 1 and it will finally result into 4 minus 1 raised to n upon n pi whole square. So the Fourier series representation, which is half range Fourier series, is given by this. Now remember over here x is valid only and only up to 0 to 1. Minus 1 to 0 was actually our imagined part to construct the cosine series of the function. So this is how we are dealing with the situation. This is given graph 0 to 1. I am adding one more part in minus 1 to 0 in such a way that it will become ultimately even by nature. So I am taking at a time minus 1 to 1 range, but whenever I have the answer, I am restricting it only up to 0 to 1. Now let us consider another part, which is half range sine series. So I will represent now the same question x square from 0 to 1 with help of sine series. So as I told you that don't get confused at the nature of the function. See, nature of the function, it is even x square, but it is not useful as the interval is not symmetric. Interval is 0 to 1. So now what will happen? I will stretch or I will extend my graph from minus 1 to 0 in such a way that it is ultimately odd function. How is it possible? See, now what we'll do, I will consider at a time that this is odd function by nature, and then at last I will give you graphical representation also. So value of c equal to 1, as I am taking odd representation, I need to find only bn's. So if I take bn, ultimately by Leibniz rule, it will result into 2 into 1 minus 1 raised to n, 1 upon n pi minus 2 upon n pi whole cube. All of you should pause and ponder at this step and then go through the calculations of Leibniz rule. 2 brackets at a time, change the sign for all upcoming values, first bracket for derivative, second for integration. And that means this is how you are representing the situation. So as I told you that the given graph is parabolic graph from 0 to 1, and then in minus 1 to 0 I am extending it in such a way that overall graph will become odd. So you can see here there is a cross quadrant symmetry or the symmetry about origin, and so it is known as odd function by nature. So I am finding actually odd functions representation in minus 1 to 1. So it will give me answer in form of sign, but then I am restricting value up to 0 to 1. And this means it will give you representation of this half range in form of sign only. So we have seen two different possibilities. It may happen that your function is given on half range and then you are extending it in such a way that it is odd, then it is represented by sign. It may happen that it is even, then it is represented by cos. So this is overall discussion about Fourier series. Now remember, this general case, even odd case or half range case, they can be for any random interval. But ultimately we have these three main categories to discuss. I hope all of you have gone through these two videos which we discussed previously for the general case and even odd nature. Then and then only you should come over here for the half range. Thank you.
LJ Institute of Engineering and Technology.